right. Hey guys, let's get this started. This is Ulan and me, Michael, and we are from the V8 garbage collection team. And we would actually like to tell you a bit of our journey with respect to our garbage collector, the rail metrics, how we measure stuff, and how we try to optimize stuff and get things faster, right? So basically, we try to give you a brief overview of how the V8 garbage collector looks like, how we see rail, how rail maybe fits into GC events. Then we would like to show you some optimizations, some results, and then maybe reflect on all of this. Maybe it was a good thing that we did. Maybe there is room for improvement and what we can do in the future, maybe better, right? So first of all, this is joint work. The GC team has grown quite a lot. So this is Hannes, Jochen, Marcel, Ulan, and me. And all of the things you see here is basically joint work. V8 and the garbage collector and rail. So this is the space we as GC people live in. Basically, GC should provide high throughput, low latency, and low memory all at once. Ideally, not consuming too much battery. For battery, we use the race to finish approach, which literature tells us it's the right thing to do. Also, hardware vendors tell us if you get things done fast, then it will be good for battery. So essentially, basically, we try to get algorithms that do all those things, and usually you have to pick a trade-off, right? So you have to either work on latency, work on memory, or maybe try to get the throughput better. How do we see the metrics and how do we see rail? I mean, ideally, you don't want to have a GC ever. You don't want to observe a GC. You want to have zero memory. That's not possible, so you prioritize. So for us, response, animation, idle, and load. Basically, for response and animation, we focus on the maximum pause time. We try to make the chunks of work as small as possible in those phases, which we determine through heuristics or API functions. And for idle and load, basically we try to optimize throughput and basically have the minimum overall GC time, if possible. For idle, there is one other fact that plays in there. We have these basically we should still be responsive, right? So there are other factors that play into this. But in general, you can say we optimize for maximum pause time and overall GC time in those phases. The fine print here is obviously not consuming too much memory. How do we do that? What do we actually measure? We measure real-world websites using Catapult or telemetry, however you want to call it. Basically, it's record and replay of real websites for mobile and desktop. And this is what we actually do for Rail. So we have, I think, a pretty good intuition on the animation part of Rail. For that, we have a set of pages that do just infinite scrolling. And while they do this infinite scrolling, we look at the GC events that happen and basically try to minimize the pause times there. For the eye, basically, we try to look at idle websites. For instance, email clients. So you open Gmail, you do a task you would regularly do, like compose a mail, look at an email thread, and then you let it sit idle. And again, watch the GC events happen and observe the pause times. Load, we are not yet there exactly, so page load is very hard to define. I've seen lots of talks here at BlinkOn, and we are waiting now for stuff to get integrated into telemetry so that we can track page load there. And actually for the R part, so we don't really have a good intuition there. We would be glad if somebody could help us out and have maybe ideas on how we could properly track R on real-world websites. It would be really interesting for us. So if you have an idea, just talk to us, right? So in order to relate all this and the metrics, we need some notion of the garbage collector, and this is really a short intro. And for all the people who have seen this slide, I apologize. We have shown it quite a lot recently. So this is the V8 garbage collector. It's a generational GC, which means that we follow the hypothesis that most objects die young and shortly after the allocation. And we have a new generation and an old generation, therefore. The new generation is collected by a scavenger, and the old generation is collected by a full mark compact collector, which actually also collects the new generation. So how does this look like? As objects get allocated in one generation, basically sometime you hit a limit. And then we copy over all the live objects into a new space. And we don't touch the dead ones, and basically we get rid of them automatically. This happens again as the space gets full again. Objects that have survived one round will be, we call it, promoted to the old generation. Happens again, and so on. So this is basically a very brief example of how the V8 garbage collector looks like. How you would observe those events like scavenger and mark compact on a trace in the Chrome tracing infrastructure. If you serialize a trace, it could look like the following. You have some JavaScript running, scavenger kicks in. It's called minor GC in the tracing infrastructure. JavaScript runs again. Then at some point, we might decide through heuristics, well, we need to do a full garbage collection, which we usually start with incremental marking. So you would see incremental marking steps, which can be interrupted by JavaScript or scavengers again. And then at some point, we are able to finalize this whole garbage collection run, and we call our full mark compact collector, which does one atomic pause and basically process the live set of objects. What did we actually do now to optimize this? Basically, we are focusing currently on the A part still, the animation part. And for the A part, the final pause is, as you can see on this pause times, is still the most critical one, as we think. So we've been introducing Orinoco through the last couple of months. What is it? It's our new GC. It's a mostly parallel and concurrent GC without strict generational boundaries, which means that objects and pages can move kind of freely between the generations. And we do that basically to fulfill the whole trade-off space, reduce chunk, memory consumption, and still provide high throughput. I will show you some features on the next slides, but a key point here is that we have been landing Orinoco incrementally, which means that you can already benefit of the features we launched. So we have split it up into smaller parts, smaller features, and we've been launching it like continuously over the last couple of months. What you see here is a UMA graph that basically shows the final pause time, the final garbage collection pause time for Android and Windows. And you can observe that jank has already been reduced there a lot. Like we have a 30% improvement on mobile and a 50% improvement on desktop, only since February, because we only track this correctly since February. So what have we been optimizing for? Basically, I want to show you two optimizations. One that fits directly into the final pause time, and one that is related to marking. So for the final pause time, most of the stuff you do is in evacuation. So you copy objects within the young generation. You move objects from new to old generation. You copy objects within the old generation for compaction, which you need when pages are fragmented. And you need to keep track of a remembered set. So you need to rewrite those remembered set pointers. Those are needed for generational GCs to keep track of old and to new references. So the general observation here is writing memory is expensive, right? And with Orinoco, we really try to have a design that leverages all the resources that are available. So what we do there is we parallelize evacuation during the final pause. Basically what this means is we perform two lock steps, and we divide all the work we have into smaller chunks, into pages. You can see those pages here. And basically, we have heuristics telling us how many additional helper tasks we can spawn. And those helper tasks will help us processing the young and old generation, the new and old generation. So this could look like we have a new generation to process now. We divide up those pages. We also have one old generation page we need to process. So we divide up those pages, and the tasks and main thread will work together on that. Then we have our barrier, and then we need to process the remembered set for our generational GC. And again, we divide up the old generation pages, which are the only pages that need to be processed there, among those tasks. I will show you an improvement soon. But this is basically what we did, and the graph I showed you, the bumps you could see in there, were basically when we launched those features. Another optimization, marking versus very busy and eager JavaScript. So it's the same event trace as before, and basically we start our major GC, we do some incremental marking, And then JavaScript comes along and allocates a lot. So there is need for allocation. This is bad because this might require doing additional marking steps. So basically, you get a bigger object graph and you need to just mark this object graph. And then you have your final GC time. The problem here is those two steps, basically. As the live feed gets bigger, you need to do more marking, and more marking potentially we have a longer finalization pause because the live heap is just bigger. How do we solve that or mitigate that or fight it? Through black allocation. It's a really cool feature. What you basically do is you assume that objects that are allocated during marking survive the following GC. This is usually true if marking goes fast. And this optimization helps making marking faster. So what we do there basically is we have our incremental marking steps. Then we sometime decide, yeah, now black allocation should kick in. What happens then is JavaScript comes along, allocates a lot, and it allocates those objects as live though. This means, that's where the name comes from, we have a color scheme and they are allocated as black. And so they are live immediately, which means that those additional marking steps might actually not be necessary, which speeds up marking a lot. And speeding up marking means that we potentially have a smaller live heap, which we can then process in the final pause. So it helps also reducing the processing of the final pause. Some results. Our favorite social website, Facebook, during the animation part. So we scroll Facebook and look at the finalization events of the Mark Compact Collector. You can see here on the x-axis is basically, you can see the Chrome version starting from 44, and on the y-axis you can see the maximum pause time. And we reduced it from around 30 seconds to, slightly above 7.5 milliseconds. As for average, we are now down to 5 milliseconds average pause time. So I think this is already quite good, and you could see that this improves. We can even see in the wild it improves using UMA. And that's basically the way we would like to go in future. Having said all that, so we looked at this maximum pause time and we tried to optimize for global GC time. The question is this the right thing to do? And I want to hand over now to Ulan for some time of reflection, and maybe we could do something better there.
Hey, so the most technical part is now over. Now comes the easier part. I'd like to reflect on the past, how we were optimizing and what's going to change in future. So the main change is how we are measuring latency. In the past, we assumed that if we reduce the post time of the garbage collector, then it automatically means reduction of latency for the user. And now, as you have seen, the post times getting smaller and smaller. And as they get smaller, we sorry. So as they get smaller, we see the limits of the existing metric, like the latency metric, the post time metric, and we would like to now find a metric that would allow us to measure latency more closer to the user, and at the same time be more actionable. Like, what is the problem with the post time? Let's start with an example. Like, let's say we have a task, long-running tasks that we want to optimize, reduce latency for. And one way to reduce latency is the hard way, to look at the task, look what is the bottleneck in the task, and then optimize it, like parallelize, make more efficient algorithms. These are the types of optimizations that Michael talked about a few minutes ago. Then there is another way, splitting up the task into smaller chunks. And it may come as a surprise, but for garbage collector, splitting up this task into smaller chunks is more difficult than to simply optimize it. And to see why, let's consider the Mark compact collector, this pose and the phases. And let's say we want to move the phase A into an incremental step. So we want to get this. This change is difficult because when we move A out of atomic pose, now the JavaScript can run between phases A and B, and at that time, JavaScript can mutate the heap. And now phases A and B need to be prepared for any changes that can happen in the heap. And this introduces a big complexity cost for the code, but it is a possible optimization. And we have plans to do this kind of optimization in future. But before we do that, we wanted to ask ourselves, is this a real improvement in latency? Will it result in user-visible latency improvement? Because there is a big cost in code complexity. What happens if these two events are inside a long-running script, as, for example, V8 execute? For the Blink scheduler, it will be Blink scheduler will not see the decrease in time of V8 execute, so it will not result in latency improvement. We could, so the other case is also possible, if these two events are a little bit further apart from each other, then it could happen that Mark compact moves out of the script, and then it's an improvement in latency because Blink scheduler now can schedule input handlers before Mark compact. So as we see, the position of these GC events affect user-visible latency. But the main metrics that we have, the garbage collection post time, is not capturing this. So this means we need a new metric. And so we are missing a metric. How we can derive that metric? We could look at what user-facing metrics are telling us, and there is a lot of work going on in defining this, what is a user-facing metric, with progressive webs and system health. I took TBM version 2 definition of what is the latency for different rail phases, and this is my understanding. So for response and animation, we track input latency. This is the time between start of interaction and when the user starts an interaction and actually sees the change on the screen. And moving this into the GC context, this tells us to minimize GC work in this time-critical window where input handling is happening. The idle phase is interesting. The metric there looks at long-running tasks, task running longer than 50 milliseconds. And then in load phase, we want to minimize time to load. So if we take these metrics as they are and make them our metrics to drive performance in garbage collector, then there is a danger that there will be overfitting. We could arrive after a few iterations at an optimal garbage collection scheduler that will try to just delay all the GC work in all non-idle phases and then post 49 millisecond tasks in idle stage, right? It will probably get a very good score in these metrics, but it not necessarily will be a robust garbage collector because it will have a lot of edge cases. So what we could do, it could simplify the model. We could say, let's for now ignore the idle phase because garbage collector should work even if there's no idle time. And let's ignore the load because it's not really latency related. Then we are left with response and animation. What is important in these phases is that we minimize GC work in critical time windows. But since we don't know when critical time window will come, we could simplify this model even more and say, let's just make this non-deterministic, and we just assume that good garbage collector should be able to handle critical time windows that can happen at any point. So given these two constraints, the garbage collector needs to do garbage collection work in order to stay below memory limit, and it needs to minimize garbage collection work in any time window. The optimal schedule would be to split up the work into smaller chunks and then uniformly distribute them over the execution time. So we don't want the trace at above, which clusters GC events. We want something more looking like trace below. So this gives us a property for a good garbage collection scheduler, that the steps are incremental and more uniform. Now the question is, can we turn it into a metric? Like, can we write a metric that takes this trace and then outputs some number saying how incremental this trace was and how uniform it was? Turns out in this case we are lucky because this problem was solved 15 years ago in GC research community. There is already a metric called mutator utilization that that measures what we want. So the name mutator comes from the fact that application is mutating the heap. Apart from the name, there is nothing really specific to garbage collector, so it can be used for any type of events. So how it works, let's consider this example with 2 GC traces. We are going to slide the window from left to right, and at every window position, we are going to record how much time is free in this window, like how much time is not used by GC in this window in percentage. Like we start off with 100%, and then as we move to the right and cover the garbage collection event, this function decreases. It is at its minimum when it's covering 2 events. Then as it moves to the right, it will increase and return to 100% again. There are 2 interpretations of this function. Like the first one is the one that I already gave, this fraction of the time GC leaves to the application in a time window. And the other one is interesting from the scheduler point of view. Like if we assume that these 2 events are top-level events, and then we know that there's a high-priority task coming in at a random moment in the current window, then the value of this function shows the probability that this high-priority task will be executed immediately without queuing. And it's related and looks very similar to another metric. It's called expected task queuing time. But the mutator utilization is simpler because it just computes probability. Now we have 2 traces, and now we have 2 functions. How we can compare, how we can tell which one is better. So we need some kind of way to extract a number from this function. One way is to look at the minimum of this function. So minimum means that the trace to the left has lower minimum, meaning that there was more clustering of GC events than the trace on the right. We also track so-called intervals with low mutator utilization. For this, we set some threshold and then look at the part of the function that is below this threshold. And on the x-axis, this will create a set of intervals. And for this set of intervals, we can now check maximum or sum and work with them as if they were pauses. To evaluate this metric, I ran the benchmark, the infinite scrolling benchmark for different versions of Chrome, and measured the post time, maximum post time of the garbage collector, and maximum interval with bad mutator utilization. And as you can see here, up until Chrome 51, the improvements in post time were also reflected in improvements in this metric. And in Chrome 51, we had regression there. And in Chrome 52, even though we improved the maximum post time, we still had regression in this metric. So what this graph is telling us is probably that now it's not worth further reducing the pause of the Mark compact. And we need to look into the different events and how they are clustered to have bigger impact on latency reduction here. So to conclude the talk, the Orinoco part, what worked really well is incremental development. So this allowed us to get very stability feedback and performance feedback really quick. For the metrics part, the main conclusion is that post time is not giving the whole story for latency, and we need, for at least for GC, to look at how the GC events are positioned in the timeline. And we hope that mutate utilization can be a good indicator of latency impact. Thank you.
Tired.
Question. Is it possible to kind of interrupt the GC running? So, for example, we are currently in an idle state, and you can run the major GC, but at any point we can switch to responsiveness because of the input event come. And so, can we just garbage collection done some work, and can we interrupt it and continue running JavaScript?
So, as I was describing in the slide about making garbage collector more incremental, interrupting it in the middle, if we don't do any GC, right? But
so I guess the short answer is no, you cannot turn off the GC, or delay it or interrupt it, but we'll make sure that, or we'll try hard to get those incremental steps configurable in some way, so that, basically you will have a safe point where Chrome can kick in again. Yes.
So have you tried comparing this mutator utilization metric with some of the input latency metrics we have? Is there any correlation?
For the input latency,
I'm wondering how does it translate to user visible latency?
Yeah, so the problem was that we have this in TBM version 2, and the main ones are in TBM version 1. But I'm also interested to look at it.
Okay, I guess we're done then. Thank you again.
Thanks.